So, hi, so today we'll start our class. So, before starting our topic today, let me uh, initially give you what are the topics that we have discussed in our last lecture, last tutorial. Okay, so in our last tutorial, uh, we have discussed about the uh, uh, molecule. We have discussed about the canonical partition function capital Q. Okay, canonical partition function capital Q. So we have basically derived the expression where this capital how basically this canonical partition function capital Q is related with the um, molecular partition function. So the relation was kind of this. So capital Q is equal to small q. Small q means the partition for molecular partition function. So capital Q is equal to small q to the power n. So this is a relation that we have established. Then this relation is true only for distinguishable particles. Distinguishable particles. Okay. Next, for indistinguishable particles, uh, for indistinguishable particles, the canonical partition function capital Q is related by q to the power n by n factorial. Okay, n is basically here is the number of particles. So this we have derived like in our last study. Then after that, what we have done, we have calculated the internal energy of a canonical partition function in terms of the molecular of a canonical system in terms of a molecular partition function, right? So initially we know that the internal energy of a sorry, let me write it in red. Internal energy. So internal energy of a canonical system is related by this relation, right? Equal to u0 minus 1 by q delta q by delta beta at constant volume, right? This you already know. Now if suppose what happens, this let's suppose the particles are distinguishable particles, so that means q is equal to q to the power n. So now we can write the internal energy in terms of a molecular partition function. So that means we need not to evaluate the whole canonical partition function, but just by using the molecular partition function we can calculate the internal energy. So the expression will now become u minus u0 equal to minus n by q into del q del beta at constant volume. Now similar way we have also proved that for indistinguishable particles also, this is for distinguishable. Now we have derived for indistinguishable particles also, like if this relation holds like this q to the power n by n factorial, then also the expression of the energy will took the same form, right? U minus u0 would be the similar minus n by q. So the internal energy will be same in both the cases. The main story in short is the internal energy will be remain same, right? The next thing is we have similar way we have also derived the entropy, right? Entropy of the system. So entropy was initially defined by this u minus u0 by t plus k ln q. Now in terms of molecular partition function, you can rewrite this thing, right, like this. This is the expression of the entropy. Okay, if you consider uh, q as for indistinguishable case, okay, you went by n factorial. If you took, then the entropy would be become this, okay, for indistinguishable, right? Now what we have done next is we have calculated this expression of the entropy for an ideal gas. Okay, so for an ideal gas, we know what is its internal energy, right? The internal energy is simply this Q minus is equal to 3 by 2 nRT for a 3D ideal gas. Okay, now if we simply substitute this thing into the expression, then this entropy will become if we substitute this after doing a few lines of algebra, the expression of the entropy will become this: n into r ln e to the power 5 by 2 v n into na by lambda cube. Okay, so this is the expression of the entropy. Here also we have considered that the particles are indistinguishable particles, so this is one of the assumption you have to take into in your account. So now, so this lambda, so lambda is nothing but the thermal wavelength that we have discussed about in several of our previous lectures, right? So lambda is the thermal wavelength, that has the expression like this: beta h square by 2 pi m to the power half thermal wavelength, right? So this whole equation is basically known as a Sackur tetrode equation. Okay, this whole equation is known as Sackur tetrode equation. Okay, so so after that we have discussed several problems where like we have like done some problems on if let's suppose the temperature and pressure is given of a gas at particular temperature, then we have derived like for different molecular mass of gas how this entropy will change. So that sort of a problem we have done in our last lecture series. Next what we have done is we have derived we have actually redeveloped the expression of the entropy in terms of volume, right? So the volume, if you write this thing, like if you like write the change in entropy in terms of volume, the delta S would simply become nR into ln VF by VI, right? VF is the final volume and VI is the initial volume here. Now what happens, this whole expression of this change of entropy we got from the statistical mechanics point of view, right? And we have also proved that in the case of thermodynamics point of view also, we will be getting the same expression. Okay, what is that we have derived using the first law of thermodynamics, right? The relation, using this relation, right? d equal to dq plus dw. From here we have actually basically derived the change in entropy in terms of volume, and that took the similar functional form that we have derived from statistical point of view. So that means so the statistical description of a system is consistent with the thermodynamic description, right? So this is basically to check the consistency we have done it. Next what we have discussed what happens if so how like physically what physically means when you change the volume. That means if you change the volume means if you increase the volume from initial to final. So according to this expression, it basically states that the entropy will increase, right? So how does that thing happen? So basically what happens here, if you increase the volume, the energy, let's suppose this is a system, let's suppose this is a 1D well kind of a system, this has this kind of energy level. So each energy level is this m square h cut square by 8ml square. So that means the energy difference between two levels are delta E is proportional to 1 by L square. L is nothing but the length of the box, right? So that means if you increase the volume of the box, that means the length of the box will also increase. So that means the density of this energy level will be also getting increased, right? So that means if you increase this length, of the box by a certain amount, then there would be much denser energy states, right? The energy states will become much more denser like this if you increase the L. Increase L. So this means that if particle gets much more energy states, that means particle will get much more configuration, right? Particles has access to much more configuration compared to the previous case. So that means the entropy of the system will also increase, right? So this is the thing we have discussed, and also we have done several numerical problem regarding this concept. Then after that what we have done, after that we have proved two important quantities in terms of the partition function, the what is that called, that canonical partition function. The first quantity that we have calculated is the Helmholtz energy, right? So the Helmholtz energy, the Helmholtz energy, it's generally denoted by A. So the expression of the A looks like this: A equal to Q minus Ts. So what I find out that the Helmholtz energy is basically the expression of the Helmholtz energy in terms of the canonical partition function looks like this: A minus A0 equal to kT into ln Q, right? So this is the expression of the Helmholtz energy. Next thing that we have calculated is the pressure. So pressure is actually this, from this Helmholtz energy itself you can actually, we have actually derived the expression of the pressure, because pressure can be written like this: minus delta A by delta V. A is the Helmholtz energy at constant temperature. This is basically the thermodynamic expression of pressure of any kind of thermodynamic system. Okay, so general expression you can say. So using this expression you can easily, as we already know the expression of the Helmholtz energy in terms of Q, that is the canonical partition function. So easily you can derive what is the expression of P will be, and that is simply P equal to kT delta of ln Q by delta V at constant temperature. Okay, and okay, so these are the some things. And next what we have done, we have actually basically verified this, whatever things we have derived, like here the pressure and the Helmholtz energy, whether it's consistent with the thermodynamics or not. So to check that, what we have done, we have calculated the pressure for an ideal gas. So we have we have considered the ideal gas with indistinguishable particles. So we took the expression of capital Q like this: Q to the power n by n factorial. And next what we have done is, next, after substituting the capital Q into this expression, and by doing some algebra, we also have used the expression of the molecular partition function, that is a small q equal to V by lambda Q, right? This is the translational partition function that we have discussed about how this Q basically comes, right? So after substituting all of this, we got the famous expression of PV equal to nRT, which is the equation of state of an ideal gas. Okay, so the main thing here is, that means that whatever things, the expression of the pressure, general expression of pressure or enthalpy that we have calculated in terms of the capital Q is basically consistent with thermodynamics. So these are some of the things that we have discussed in our previous tutorial class. So now today's class we will start from the okay, so we will start from the enthalpy, because two of the potential are still required to verify, to calculate. So one of them is the enthalpy and the other one is the Gibbs free energy, right? So we will start from the enthalpy. So before that, let me write the previous expression of the thermodynamic potential. That is, first the internal energy is U minus U0 is minus del ln q by del beta at constant volume. Second relation is the pressure relation, equal to kT by delta ln q by delta V at constant temperature. Now from here we know from thermodynamics the expression of the enthalpy looks like this. So enthalpy H equal to U plus PV, right? So now H minus H0 equal to U minus U0 plus PV, right? Now from here what you can do, U minus U0 you already know, and the expression of the pressure already we know. So just you have to substitute this to expression here. So after substitution we'll be getting H minus H0 equal to minus delta ln q by delta beta at constant volume plus kTV by delta ln q by delta beta at constant temperature. So we got the expression of the enthalpy, the expression of the enthalpy. Okay, now now we'll go, so we here also we will do the similar thing that we have done in the previous cases, where we have substitute the capital Q in terms of small q, and after doing that we will also verify what will be the case for an ideal gas to check whether it's consistent thermodynamics or not. So similar recipe also applies here also. So first we will take capital Q equal to Q to the power n by n factorial. Now if you substitute this expression into the expression of the enthalpy, you will be simply getting H minus H0 equal to minus delta ln Q to the power n by n factorial by delta beta, that is at constant volume, plus kTV into delta of ln Qn by n factorial by delta beta at constant temperature. Now you have to do a bit mathematics here. So so the first term will be decomposed into two terms, right? So the first term will become n into delta ln q by delta beta at constant volume plus minus, so there is a so n factorial is in denominator, so minus will become plus, so delta ln n factorial plus delta beta at constant volume. The next term will come kTV equal to kTV into n into delta ln q by delta V at constant temperature minus delta ln n factorial by delta beta at constant temperature. Now if you do the mathematics again, it will gives you, so this derivative of ln n factorial with respect to the temperature of the beta is simply will be 0, because n factorial is nothing but just a number, right? It's a constant number, so the derivative will gives you 0, right? So H minus H0 will now become n by q delta q by delta beta at constant volume plus n k TV delta ln q by delta beta at constant temperature. So this will be the expression of the enthalpy we will be getting. Now the thing is, so for a 1D what is this called, for a 3D system, the translational partition, the q is nothing but a translational partition function. So the expression of this translational partition function you already know is beta by lambda q, right? Lambda is a thermal wavelength. So if you substitute the small q here into the expression of the enthalpy, the expression will now become like this: n minus n by v into lambda q del v by lambda q by del beta at constant volume plus n k t v into lambda cube equal to del v by lambda q into del v at constant temperature. Now after doing all the calculation, H minus H0 equal to now become n by v lambda cube into v del beta of 1 by lambda cube at constant volume plus n kt lambda cube by lambda cube, so lambda cube will cancel. Now if we do the further simplification, this will become h minus a0 equal to minus n lambda cube by lambda to the power 4. There's a minus 3 will come because I'm doing the derivative of 1 minus lambda cube. Then it will become 1 lambda by del beta at constant volume plus nkt. Okay, now now the next thing that you can do, yeah, okay, so so lambda cube is here become, so this will become 1 by lambda. Now next thing what you can do, lambda is basically this, right? Lambda is beta h square by 2 pi m to the power half, thus the expression of the thermal wavelength, right? Now if you do the derivative of lambda with respect to beta, so d lambda d beta is equal to beta h square 2 pi m, right? Yeah, sorry, one second. So no, this will be minus half into minus half to the power minus half. Yeah, now it's fine. So that delta lambda delta beta you can calculate. Now I have to substitute delta lambda delta beta into here. After doing that, h minus h0 will become 3n by 2 lambda into beta h square by 2 pi m to the power minus half into beta h square 2 pi m into 1 by beta plus nkt. So next thing, h minus h0 will now become, now what you have to do next in next step, this you can see there are a lot of terms that will be simply terminated each other, so terminates each other. So if you cut those terms, now then the whole expression will become 3n beta, this thing, this lambda is also there. If you substitute the expression of lambda, so this whole things will be cut, and this will become 3n by 2 beta, okay, plus n kt. Okay, now if you write the expression of beta, h minus a0 equal to 3 by 2, beta is kt, so n kt plus nkt, so it will become 5 by 2 nkt. Okay, now n is, we know, the total number of particles, right? So we can write this total number of particles in terms of joule and Avogadro number, right? So n can be written, n that is joule plus na, that is the Avogadro number. So h minus h0 will simply turn out to be 5 by 2 into n into na kt. That means 5 by 2 n, na into k is the r, the ideal gas constant, into T. Okay, now you know 5 by 2 nRT, right? Now this we got the enthalpy of an ideal gas. So now the enthalpy has like, why you are basically calculating the enthalpy, right? Because if you know, enthalpy has many applications. Okay, one of the very important application of enthalpy is you can basically calculate the specific heat of a system at constant pressure if you know the enthalpy of the system, right? We have also derived this thing previously, right? So Cp, specific heat at constant pressure, is simply related with the enthalpy by using this, right? Cp equal to del H del T at constant pressure. How it's coming? So we know H equal to U plus PV, right? So dH equal to du plus pdv plus vdp. So du equal to dq plus dw, right? So du dq you know is tds plus pdv. Sorry, this is dq equal to du plus dw. Yeah, now it's fine. So dq equal to du is, so du equal to dq minus dw. So du equal to dq is tds minus pdv plus vd minus vdp, right? Minus pdv. Yeah. So now if you substitute it here, okay. Okay, GW is minus PDB, so minus minus will become plus. Okay, now it's fine. Okay, so DH you can write is as, so it will become TDS. So PDB PDB will cancel, VDB VDB will cancel, it will become PDB. Now that means the CP will become, CP is nothing but the CP is nothing but du dq by dt at constant pressure, right? So if you write in terms of dp, so dq now become here, then this will become cp equal to become dh by dt at constant pressure, right? So this is how this whole expression is coming now. uh, so so if you know the enthalpy, so you can easily calculate the cp. So cp will be become, here enthalpy we got 3 by 2 nr, 5 by 2 nrt, 5 by 2 nrt, it will become 5 by 2 nr. This is the expression of the cp. Now cp minus cv is equal to r. So if you know the cp, you can calculate the cv. Cv is equal to 3 by 2 nr, right? Which is consistent with the thermodynamic result. This is actually 3 by 2 nr is the actually the specific heat of a ideal gas, right? So anyway, this is true. Now we'll do some so what we have done, so we have started from the thermodynamic expression of the enthalpy, that is a minus a0 equal to minus kT ln q, capital Q. From there we are using the expression of the pressure to get, sorry here, so to get the expression of the enthalpy like this. Now from there uh, this is the expression final. Now from there we are basically substitute the expression of the capital Q, that is the partition function, that is the canonical partition function expression in terms of small q. After doing the substitution, we will getting h minus a0 equal to delta ln qn by n factorial this after doing the derivative h minus a0. After doing the derivative here in the right hand side, we are getting the expression of h minus a0 like this. Now here next what we have done, we have now know that we already knew, right, what is the translational partition function of a monatomic molecule if it's moving inside of a chamber, 3D chamber or box. Then the h minus a0 would be simply this expression. Now if we do the further mathematics, at the end, for an ideal gas, the enthalpy will take the form like this. H minus H is equal to 5 by 2 nRT, right? Now from here, first thing what we can calculate is the Cp thing, right? So Cp is first the derivative of the H, so 3 by 2 nRT. If you do the derivative, Cp will take the form Cp equal to 5 by 2 nR, right? So this is how you can calculate the specific heat. If you know the enthalpy, you can calculate the specific heat at constant pressure, right? Next thing is enthalpy and heat transfer. Okay, so we will do some problem now. Okay, so first problem is, so problem one is, for a reversible process at constant pressure, prove that dqp equal to dh. Okay, so and next in the problem it has been asked to find out and explain why enthalpy is a measure of heat content under constant pressure condition. Okay, so the first thing is here, what you can do, we will first write the expression of the enthalpy, thermodynamic expression of the enthalpy, right? So we already know H equal to, what is this, H equal to, yeah, H equal to U plus PV, sorry, PV. Okay, now if you take the small change, dH equal to du plus pdv plus vdp. Okay, now we already know the expression of so the expression of du is basically TdS at constant pressure, right? Okay, so we will simply substitute it here. After doing that, dH will become dH will become, so if you put, so it's in constant pressure condition, right? So change in pressure will be 0, so constant pressure, so dP would become 0. So that means dH will become simply TdS plus VdP, right? So one second, so here, okay, okay, so So here what we are doing actually, du plus pdv, right? So dq equal to du plus dw. So we are putting dq equal to du plus dw already needs pdv. Okay, so you are substituting basically this dq here. After doing that, we are writing dh as dq plus vdps. Now from here, uh, what you can write, uh, dq. So if the pressure is constant, so dp is constant, so we have to substitute dp here. After doing that, we can write dh as dqp. Okay, so this is basically the expression of the change in enthalpy, which is basically equal to the change in the amount of heat at constant pressure. That actually tells us that entropy is nothing but, so this basically tells us, if someone asks you the proper definition of enthalpy, this is one of the many ways, okay, where like by using which you can explain. So enthalpy basically represents the heat absorbed at constant pressure. Okay, fine. So we got the expression of the entropy here, enthalpy here. Now comes the say problem number 2. So problem number 2 states that enthalpy of ideal gas. Okay, so starting from U equal to CVT for an ideal gas, derive the relation, H equal to U plus PV equal to CPT. So this relation you have to prove for an ideal gas, given the fact is the expression of the internal energy is following this kind of a relation with CV and DT. So anyways, so yeah, so we will do that. So in order to do that, first let me write the known expression of enthalpy, that is H equal to U plus PV. Now here the expression of U is already given, that is U equal to CV into T. Now if you substitute it here, so H will now become CV into T plus PV. Now given the fact is that this system is an ideal gas system, so we can use the properties of the ideal gas, right? So for an ideal gas, we know PV for an equal to nRT. Okay, uh, let's for the case being, let's consider we will be considering 1 mole of gas. Okay, considering 1 mole of gas. So that means the PV will become simply equal to RT. The N is becoming 1 here, and the N will be equal to 1. So H will now become as CVT plus PV, you can write now as RT. So now H will become, if you take T as common, then CV plus R. So we already know Cp minus Cv equal to R. So Cp is equal to R plus Cv. So this means H equal to T into Cp. So the expression of the enthalpy we got, H equal to Cp into T. what is the expression? This is basically the expression of the enthalpy. Okay, yeah. So now, the second thing, so we have already derived we have derived the concept of enthalpy and also done some problem on it. The next thing that we'll be trying to derive, the last thermodynamic potential, and also a very important one, that is known as the Gibbs free energy, right? Uh, Gibbs free energy. So, so, so why I'm telling this Gibbs free energy is a very important quantity, because um, in a process, in any kind of process, in a chemical process or any kind of process that is happening in our universe, so that process is said to be spontaneous only if the change in the Gibbs free energy is less than zero at a constant pressure and temperature. So so that means by changing by calculating the change in Gibbs free energy, you can basically predict whether this process would be is the what like the process is a spontaneous process or a not spontaneous process. So so that's why Gibbs free energy plays a very important role. Okay, so let me write it. uh, Process is said to be spontaneous if the change in Gibbs free energy, that is delta G, is said to be less than zero at constant pressure and temperature. Temperature. So so let me first write what is the thermodynamic expression of the Gibbs free energy. So the Gibbs free energy expression is simply looks like this: G equal to basically H minus Ts. So you can write it. There are several other ways also. You can write the Gibbs free energy. One is this. The next one you can write it like this also: A plus PV. So that means uh, how this basically is coming. You can basically write H equal to U plus PV. From there minus Ts is there, so now G equal to U minus Ts plus PV. U minus Ts is nothing but A, so from here you're getting this, because A equal to U minus Ts. Okay, so the main thing is you can write the Gibbs free energy uh, in terms of several kinds of other thermodynamic potentials. So now what we'll do, the same thing, we will write this Gibbs free energy in terms of first in terms of canonical partition function. Then we will derive the expression of Gibbs free energy in the case of an ideal gas, and check and we'll be checking what will be its expression basically, and we also do several problems from here also the same way. So free energy you can write G minus G0 is simply A minus A0 plus PV. Okay, now G minus G0, we can write this A minus A0 as minus KT ln Q plus, sorry, plus PV. So A minus A0 is minus KT ln Q, which are being used here. So this expression we got in our previous derivations, right? So this is basically the expression of the Gibbs free energy in terms of canonical partition function capital Q. Now what we will do next is we will derive this expression of Gibbs free energy in terms of uh, molecular partition function, and for an ideal gas, okay, where the particles we are considering is basically indistinguishable. So calculating Gibbs free energy G for ideal gas where the particles are indistinguishable. So for that, uh, so so first what you can do, you can write capital Q equal to Q to the power n by n factorial. So G minus G0 would be minus KT ln Q to the power n by n factorial plus PV. PV we can write it as so for ideal gas, for let's suppose 1 mole of ideal gas we are considering here right now. So for that case, PV simply you can write as RT. So now if you substitute it here, so G minus G0 will become minus KT, this whole thing, then plus RT. Or you can also keep the expression of the moles also. Okay, so nRT is fine, nRT. So G minus G0, this will help us later on. So G minus G0 will become now KT ln Q to the power n plus KT ln n factorial plus nRT. Now here if you do, if you have to use the Stirling approximation here for a very large number of n, for very large values of n. So KT will now become NKT ln Q plus, so ln n factorial will become n into ln n minus n. Ln n factorial, we are writing this thing like this plus nRT. Now what we'll do, we will simply write G minus G0 as NKT. So n is basically number of moles into the Avogadro constant, right? So Avogadro constant into K is equal to R. So Na into K is equal to ideal gas constant R, right? So we can write this whole thing like this: nRT ln Q plus, here also NKT you can write it as nRT ln n minus nkt you can similar way write nrt plus nrt. So nrt will basically cancels each other. Then you can write g minus g0 as equal to minus nrt ln q plus nrt ln n. So now we can write g minus g0 equal to, so you can take nrt as common, minus nrt let's suppose. Then you can write ln q by n. Okay, yeah, you can take minus, so this will become minus, so n will go to the denominator, so g minus g0 will getting this. So this is basically uh, the expression of Gibbs free energy, the change in Gibbs free energy in case of an ideal gas. Okay, so anyway, so this is a very also straightforward way. So we have started from the expression of the Gibbs free energy in terms of other thermodynamic potential, whose expression we have already derived previously. So there's those expression we are using. So those expression is usually g equal to h minus ts. So from there we are writing this h minus t, so writing like this, g equal to a plus pv. And after that we know the expression of a and p. P is not required right now because we are calculating for the case of an ideal gas, so we are simply use the relation, the equation of state for an ideal gas, which is pv equal to rt. So we keep, so that's why I keep the pv term as it is. So g minus g0 equal to a minus a0, so a minus a0 we already know, minus kt by ln q. Q is the canonical partition function here, and the PV term retains here also. Next, you're substituting the capital Q here into the expression of the Gibbs free energy. So G minus G0 equal to minus KT ln Qn by n factorial plus nRT. So nRT comes from this relation, this ideal gas relation, PV equal to nRT. Now from there itself, what we are doing, G minus G0, we are basically expanding it into in terms of log plus nRT, then g minus g0 we are writing like this. Then after doing several what is this called, several algebraic manipulation and all, we are getting this kind of relation of Gibbs free energy in terms of molecular partition unit Q, temperature, and the number of particles. Okay, now having said that, we have now the expression of the Gibbs free energy. Now we simply do some problems that is mainly related with the potential, thermodynamic potentials. That is basically it's more focused on the Gibbs free energy and the Helmholtz free energy. Okay, so the first problem is problem number 1. Calculate the pressure and entropy in terms of Helmholtz free energy. Okay, so yeah, so the starting point is pretty much same. First write the expression of Helmholtz free energy, which is basically this. Helmholtz free energy expression is this, A equal to U minus Ts. So now we will take the differential form. dA is equal to du minus tds plus minus s dt. So now we know du equal to sorry, dq equal to du plus dw, right? So that means du would be dq minus dw. So du is basically, dq is tds and dw is pdv. Okay, these things we are using from the first law of first law of thermodynamics. Yes. So this will simply uh, substitute this expression into this expression of the Helmholtz energy. After doing the substitution, we will be getting dA equal to du, we know, is tds minus pdv minus tds minus sdt. So now dA will become, so tds will be simply getting cancelled. So dA will be getting like pdv minus sdt. Okay, this would be the expression of the dA. Now from here what we'll do, we will simply write the pressure. So writing the pressure in terms of okay, so from this result itself, you can write this pressure in terms of the Helmholtz free energy. That would be P equal to dA by dV minus, that will be minus sign at constant temperature. Similarly, the entropy you can write as minus dA by dt at constant volume. Okay, so these would be the suffice expression to basically express the pressure and entropy in terms of the Helmholtz free energy. Okay, now, so this is a very straightforward, not very difficult thing to do. First you have to write a Helmholtz free energy expression, then from there you have to write a differential form, d equal to du minus tds minus sdt. Now from there what you have to do, you have to basically substitute the expression of the du that you already know from the first law of thermodynamics, that is du equal to tds minus pdv. So that expression you have to substitute here. So du equal to tds minus pdv. If you substitute it here, d equal to tds minus pdv here, so there you will get d equal to tds minus pdv. So tds will cancel, so that you will be remain with minus pdv minus sdt. So from this differential form you can write p as dA by dV and entropy as dA by dt. To support, like, this dA is basically a state function, so to make this whole differential form as an exact differential form, this relation should be maintained, right? So yeah, so this is the way you can basically express the pressure and entropy in terms of the Helmholtz function. Next, there is another problem number 2. Okay, so the problem 2 is calculate the volume and entropy in terms of Gibbs free energy. Okay, So the same strategy will be used here also. So first thing is you have to write the thermodynamic potential gives free, that is the gives free energy in terms of the known potential that you already that their expression that you have already know. So G would be simply equal to H minus Ts, where H is basically the enthalpy here. Okay, so H minus Ts, so you can write dg equal to H is the enthalpy here. Okay, so in the expression of the enthalpy we have already known from our uh, previous discussions, right? So first thing we have to write this expression in terms of in the differential form. Dg will become dH minus TdS minus SDT. So dg will become, so H we already know, H is U plus PV, right? So dH is du plus PdV. Yeah, sorry, U plus PV, if it's PV, then dH equal du plus PdV plus BdV, and du is we know TdS minus PdV. So dH equal to du we already know is TdS minus PdV plus PdV minus plus PdV plus PdV plus VdP, yeah, plus VdP. So dH is now PD minus PdV plus PdV will cancel, so dH will become TdS plus VdP, right? So the expression of dH you have to substitute here also. After doing the substitution, we can write this TdS plus VdP minus TdS minus SDT. So now here TdS will cancel. The remaining term is VdP minus SDT. So now from here what you can do, we can write the V, that is the volume. You can write the volume as del G by del P at constant temperature. Similarly, the entropy you can write as del G by del T at constant pressure. Minus n would be there. So this is the expression of volume and entropy you can write in terms of the Gibbs free energy, right? So yeah, so okay, so how we have done it, so let me recapitulate. So G we have write in terms of the known thermodynamic potential, that is H. The other are the basically some simple coordinates, T minus Ts. So dg I am writing dH minus TdS minus SDT. So dH expression you already knew, that is this. If you substitute the expression of du and doing all of the algebra, then you will be getting dH as TdS plus VdP. Now I have to substitute this thing here into the expression of dg. After doing the substitution, you can write the dg in terms of like this, dg equal to VdP minus SdP. So from there you can write the volume as del G by del P at constant temperature, and entropy as minus del G by del T at constant pressure. Okay, so that is how we can calculate the volume and entropy in terms of the Gibbs free energy. Okay, next what we will calculate, what we will do is a different thing. So we are basically done with all this kind of thermodynamic potential. Okay, we will start it from internal energy, then from there we have derived the entropy, and we have also calculate what is the value for ideal gas as an application, and we find out that it's basically the consistent with the result that we got from thermodynamics. Then after that we have also derived other potentials also, like first we have done for enthalpy, the next we have done for the Helmholtz free energy, and lastly we have done it for the Gibbs free energy, right? So for all kinds of free energy and thermodynamic potentials, also I've done it for pressure also, how the pressure is dependent on the canonical partition function, and also normal molecular translational molecular partition function. Okay, so all of these things we have done so far. Now the next thing what we will do, so since now we have only considered the systems, monoatomic systems, where there is only one type of one contribution from, there is only a single contribution in the partition function, that is from the translational component is coming, right? There are also other component that is related, that is there in the expression of the partition function, like the rotational partition function, vibrational partition function, electronic partition function. Okay, so far in our previous discussion we only considered the translational partition function, since we only consider monoatomic systems as a very simple system. But now we will see what are the implication if the rotational motion is involved into the system. So that means there would be a term that would be contributing as a rotational term into the partition function expression. So we will basically derive it and we will see how it looks like. So for that let me first write. So let me first write. So in the energy of a molecule, different modes of motion will make the contribution. Okay, now uh, so let's suppose the energy of a jth molecule EJ equal to EJ, one contribution is coming as translational, one contribution is a rotational, one contribution is vibrational, and one contribution is electronic. So this is translational, this is the rotational component, rotational, this is the vibrational, and this is the electronic contribution. Okay, so if this is a general expression of the energy of a molecule, then from this expression you can write the expression of the partition function, right? So general expression of the partition function will be looks like this. A molecular partition function will be looks like this: E equal to summation over J, that means all the energy states for different modes of motion we are considering. So E equal to summation over J into e to the power beta. The first will be EJ translational plus EJ rotational plus EJ vibrational, then EJ electronic. So 4 contributions are there. Now from here we can write Q as summation over J e to the power minus beta EJ translational into summation over J e to the power beta EJ rotational into summation over J e to the power beta EJ vibrational into summation over J e to the power beta EJ electronic. So these are basically the 4 contributions that are contributing to the molecular partition function of the system. So the partition function Q now becomes as Q translational. So this term we are considering is the translational contribution into the total partition function, and we have termed it as QT. Second part, second contribution comes from the rotational, we are terming it as QR. The third one is the vibration, we are naming it as QV. And the last one is the electronic, which are denoting as QE, and this is comes from the last contribution, which is the electronic contribution, right? So this is the expression of the partition function Q, total partition function Q. Okay, now so far what we have discussed is the case where the particle is, let's suppose a monoatomic particle is moving in a 3D volume. Okay, like this 3D volume it's moving. Then for that case we have uh, calculated its, what is this called, this partition translational partition function, that is QT. It's a molecule moving, sorry, it's a, let me write it properly here, monoatomic molecule moving in 3D box with volume V. For that case the partition function looks like this. uh, Lambda equal to h by beta 2 pi m half, sorry, this is not, this is thermal wavelength, sorry. So the partition function, the molecular partition function looks like this, q equal to v by lambda cube, right, where v is the volume of the container and lambda is the thermal wavelength. So thermal wavelength so lambda is the thermal wavelength here. So the expression is of lambda looks like this, h by under 2 pi m kt. Okay, okay, okay. So now this is only true for monoatomic cases. Okay, so now if you consider diatomic cases, so these are only possible, this only the translational contribution of the uh, partition function is only applicable for monoatomic molecules. Okay, like helium, argon, this kind of molecules. But let's suppose for diatomic molecules, diatomic like iodine or H2 or bromine or triatomic or multiatomic, whatever, like more than one atoms are involved in the molecule. So in that case we have to consider the rotation of the system, right? So the thing is, like, the molecules, the atoms in the molecules are like connected like this kind of structure, right? That means a dumbbell kind of a shape in a, for a, this is for the case of a 2D, for a diatomic. Similarly for triatomic case it would be like this, something like this, right? These three are basically the atoms. So this means it's a kind of a dumbbell kind of a shape, right? So that means it would rotate, it has an orientation particular, right? So that means as there is rotation into the system, so that means you have to consider the rotational partition function into the system. Okay, so first what we'll do, we'll consider the linear rotor. Okay, so we'll take first a diatomic system. We will take a very simplistic case initially. So we take a non-symmetrical linear rotor. Okay, the concept of a non-symmetrical linear rotor. Okay, so first what we'll do, we'll calculate the partition function of a non-symmetrical linear rotor of type AB. That means that means a diatomic. So A R B, it's like connected like this. This A R B basically the atoms in a molecule. So anyway, so the energy, okay. So the energy levels of linear rotors are related with EJ equal to HCB into J to J plus 1. So this expression is already is a very well-known expression of energy, energy of like the different rotational energy levels. So let's suppose we here also quantize the energy level like this, the rotational energy level. J has starting from 0, 1, 2, 3 like this. So these are the basically energy level J 0, 1, 2, 3 like this. And here B is the rotational constant. Okay, so B is here is the rotational constant. Okay. So value of B is already mentioned in the literature, which is h cut by 4 pi Ci. Okay. Here I is the moment of inertia, because moment of inertia, because the rotation is involved, right? If rotation is involved, so that means the moment of inertia would be involved into the system, right? So when you give force at a particular point from the system center of mass, then in order to calculate its angular movement, you have to first know what would be its moment of inertia, right? So for that sense, the expression of the moment of inertia of that particular molecule is actually required, and the expression of this for this kind of linear rotors, the expression of the moment of inertia looks like this: mu equal to r square, where mu is the effective mass, okay, and r is the bond length here. This thing actually in actual experiments also you can actually calculate these things, like the mass of the atoms or the bond length. These are actually the quantities that can be done by experimental calculation. So If you know the values of those quantities, then from there, for a linear rotor kind of a molecule, you can easily calculate the what is this called, the rotational energy levels. Okay, the rotational energy values are different energy levels, right? Now, okay, so the rotational term, so QR would be looks like this. QR would be summation over J Gz. So Gz is the degeneracy factor. So what happens in this rotational energy levels? These are not single degenerate. This is multiple degeneracy associated with each energy level. So the degeneracy number is noted by Gz. The expression of the Gz looks like this. G is equal to 2j plus 1. So QR equal to summation over j equal to 0 to infinite Gz is simply 2j plus 1 into e to the power beta ej. So ej equal to, yeah, so ej, you already know the energy of the jth state is basically hcb is the rotational constant, j into j plus 1. This is the expression of the energy ej. So now from here, so if you substitute the expression of the ej into this expression of the rotational partition function, then this expression would be turn out to be j0 to infinite 2j plus 1 e to the power beta ej is simply hcb into j plus 1. 2j plus 1 we already discussed the degeneracy factor. Let me write it here also, degeneracy. Okay, so if let's suppose the energy states are very closely distributed, it's looks like not a discrete energy levels. If the number of the density of energy states are very high, then instead treating the energy state as a discrete energy state, we can make the energy state as continuous state, right? If let's suppose energy states are very close, so then instead of using the summation, we can use the uh, integration integration here. So we can write QR as integration 0 to infinite, so j starts from 0 to infinite 2j plus 1 e to the power beta hc by b into j plus 1 into dj. Okay, so this is the expression of the rotational partition function QR. Now from here we will use some concept of mathematics. We will so to simplify this expression, what we will do first, we will use this result, the derivative of e to the power beta hcb j into j plus 1 with respect to j, and we will use this result in the later case. Okay, expression beta hcb 2j plus 1 into e to the power minus beta hcb j into j plus 1. Okay, so this is basically the derivative of e to the power beta hcb j into j plus 1. So this expression we will be using into the expression of the QR. So so this expression now looks like this. Two j plus 1 e to the power minus beta HC B J into J plus 1 is this. So okay, is equal to, okay, so this is equal to, that means minus 1 by PHC beta into DDJ of to the power beta HC B J into J plus 1. Okay, so now, okay, so yeah, so this expression, as you can know, this expression is already used here. Okay, so we can write this thing in terms of a derivative. So this will make the integration simple. Like we will then approach the integration, which will be not that much complex, right? If we write the whole thing in terms of a derivative. Okay, so Q1 would be, Q rotational would be minus 1 by P, it's 1 by beta, sorry, 1 by beta HCB integration b del J of e to the power beta HC P J into J plus 1. Now here, so basically we are substituting this thing in terms of derivative here, dj. Now here if you do the integration, you will getting qr equal to 1 by minus 1 by beta HCB. Now from here, yeah, okay, so the integration limits running from 0 to infinite, 0 to infinite. So okay, so now okay, so think, okay, here QR is 1 by minus beta HCB into summation is 0 to infinite, and here it would instead of this derivative term we can write this thing directly, e to this e to the power term. Okay, so it would be become e to the power beta HCB J into J plus 1 dj. Now here if you do the integration again, it will become QR equal to minus b HC beta into q to the power beta HC beta j into J plus 1. Integration runs from 0 to infinite. If you do the integration, if you substitute the value, you will getting 0 to infinite. So QR would be simply become b minus minus will become plus beta HC b 1 minus 0. Okay, so QR is rotational would be 1 by beta HC b. B is the, so B is the rotational constant here. Okay, and here we will be using some of the quantities, like we are considering a temperature called uh, rotational temperature. So this thing, this expression of the QR is only valid above uh, above a certain temperature. So we are considering theta as the thermal, theta as the rotational temperature, because this whole expression is depends on the temperature, so we have to define the theta. So theta is the rotational temperature, The expression of the theta, you can write it like this: K into theta equal to HCB. High temperature means that basically suggesting you to take T is greater than equal to theta. Okay. Now we will do some problems. Okay. So the problem number 1 is for a linear rotor CO, compute the Q rotational. Okay. So we know the expression of QR is like this: QR is 1 by HC beta B. Now I've defined a temperature called the rotational temperature, that is theta R equal to HCB by K. Now if you substitute it here, then the QR will become, in terms of rotational temperature, then it will become K by, become beta is already in a KBT, beta is 1 by KBT. So if you substitute beta here and expression of theta R in terms of HCB and K, then it will become as QR will become T by sigma theta R here. Okay, so here theta also you can write, so theta also you can write it like this also: theta equal to basically h cut square. If you substitute the expression of B also we know here, right? B equal to h cut 4 pi Ci. B equal to h cut 4 pi Ci. Now if you substitute the expression of B here, so you will be getting the expression of theta like this: theta equal to 2i kb. Kb or normal K, that's the Boltzmann constant. And I you already know is the mu r square. Mu is the reduced mass Okay, here there are two molecules are there. One is the carbon and one is the oxygen, CO. So their reduced mass will be like this: Mc into Mo plus Mc plus by Mc plus Mo. And here the sigma thing, sigma is basically a factor. Okay, that is equal to 1 for heteronuclear and sigma equal to 2 for homonuclear. So for this problem, as both the molecules are different in nature, both the atoms or the nucleus into the molecule are basically different, coming from different material element. So that means a heteronuclear system. So we can take sigma equal to 1 here. If it was homo like O2 N2, then the sigma, we have to take sigma's value equal to 2. So having said that, so we have most of the info. So the given information is for CO, the given is given for CO, bond length is mentioned. So you can calculate the moment of inertia and all, 1.128 angstrom. The mass is also given, so it's easily calculable. Masses are Mc equal to 12U, and masses other is the oxygen mass equal to Mo equal to 16U. U is basically the atomic mass units. So using the high temperature for a linear molecule. So okay, now in the problem actually you have to calculate the the rotational partition function at two different temperatures. Calculate the Q rot at T equal to 300 Kelvin and 1000 Kelvin. Okay. So this is the information supplied, and Q rot you have to calculate. The first thing we'll do, we'll calculate the moment of inertia. In order to do that, we have to calculate the reduced mass and using the bond length. Okay, so reduced mass mu equal to 12 into 16 by 12 plus 16 equal to 6.857 U. Okay, that means 1 U is basically 1.38 into 10 to the power minus 26 kg. Okay, atomic mass unit U. Now okay, so you have calculated the mu. Now from here you can calculate the moment of inertia I, that is mu r square is simply 1.138 into 10 to the power minus 26 into 1.128 into 10 to the power minus 10 whole square. So I would be simply become almost equal to 1.45 into 10 to the power 46 kg into meter square. Kg into meter square. So that means theta, the rotational temperature will become h cut square 2I kb equal to almost equal to 1.055 into 10 to the power. So h cut square is, we already know, 1.55, 10 to the minus 34. That whole square into 2 into I value we know, we have calculated, that is 1.45 into 10 to the minus 46 into kb is the Boltzmann constant, 1.38 into 10 to the power minus 23. That means theta r would be simply almost equal to 2.78 Kelvin. It's very low actually, not that much high. So Q rotational would be, that means simply T by theta r, sigma is 0. T by theta r, that means 300 by 2.78, so that gives you 108 at 300 Kelvin. Next case, Q dot would be T by, that is at 2000 Kelvin. For 1000 Kelvin it would be 1000 divided by theta r, that means 1000 divided by 2.78 equal to 360 almost. Okay, so these are the values of the rotational partition function, okay, for two different temperatures. So what we have done here basically, so in the information we already see, so we have to first calculate for a heteronuclear molecule CO, we have to compute the Q rotational. But in the information, the things that are supplied is bond length, masses and temperature. So we have to write the whole expression of this rotational partition function in terms of this given the supplied values, supplied variables, right? Sorry, supplied parameters. So we write we first write this theta, that is the rotational temperature, in terms of moment of inertia I, that we can easily calculate since the masses are given and the bond length are given. So after calculating the theta r, we only need T, that is also supplied, and for heteronuclear we are taking sigma equal to 1. So next thing, we have calculated the mu. From mu we have calculated, mu is a reduced mass, and from there we calculate the I, the moment of inertia, and from there we have calculated the theta, the rotational temperature, which is about 2.78 Kelvin. Now if you know the rotational temperature, from there itself you can easily calculate the Q rotational for two different temperature, 300 and 1000 Kelvin, and these are the values you got here. Okay. Okay, so this problem is now done. This is problem number 1. Similar way, so now so the problem 2, it has been calculated for a linear rotor calculate population ratio between j equal to 0 and j equal to 1. Okay, and the supplied information is theta is given 20 Kelvin, and the temperature at which we have to calculate, that are also mentioned, is 10, 50 and 300 Kelvin. Okay, so now the population density for like each state that we have done. So these are the basically the population levels, right? Okay, so let me just copy these things. E to the power. So population at j equal to 1 and population at j equal to 0 is simply g1 by g0 e to the power beta ej e1 and e to the power beta e0. Now expression of the ej looks like this. So ej is hcb into j plus 1. So at a particular energy state j, hcb j into j plus 1. Okay, now from here okay, so now we have to write this hcb in terms of theta r. Okay, so theta r is basically k theta r, right? Yeah, you can see here from this theta r equal to hcb by k. So as theta r equal to hcb into k, so you can write ej as k into theta r into j plus 1, and g1 is a degeneracy, that is j into j plus 1. What is the degeneracy? Let me see. 2j plus 1, sorry, the degeneracy was 2j plus 1, so gj was 2j plus 1. So the population would be, so ej is theta, so population would be pj equal to 1 by pj equal to 0 would be simply g1 is 1, g1 is basically, sorry, g1 would be 3 and g0 would be 1, and e to the power minus beta ej minus e0. Okay, so now from here, so ej is k theta r. Okay, so e1, sorry, yeah, now it's fine. So now here if you substitute it, so here if e1 minus e0 would be simply nothing but 2k theta r, right? So that means you can write pj equal to 1 by pj equal to 0 like this, 3 into exponential to the power beta means kk, so beta is there, minus beta k 2k theta r. So beta, from beta k will get cancelled, so e to the power exponential 2k theta r by t, pj equal to 1 by pj equal to 0. Okay, so this would be the expression of 3 is there, so this would be the expression of the population. Okay, now in the problem itself it has been asked to calculate the fraction at particular temperatures are given, okay, for that temperature only. So in order to do that, first let evaluate for t equal to 10 Kelvin. Okay, so for t equal to 10 Kelvin, that would be p1 by p0 would be 3 into exponential minus 3, k is the Boltzmann constant 1.38 into 10 to the, what is the Boltzmann constant value, 10 to the power minus 23, yeah, 10 to the power minus 23 into theta is given, theta value is given, that is 20 Kelvin by 100. Sorry, I think in the expression, okay, kk will get cancelled, so k would be not there here. Okay, yeah, so sorry, Yeah, now it's fine. 3k theta. K will cancel. Okay, yeah. Now it's fine. It's 3. Oh no, so it's 2. 2 into theta. Now it's fine. Yeah. So it would be 2. 2 into 2 into 20. Yeah, now it's fine. So P1, P0 equal to 3 into exponential to 14. So it will give you minus 4. So it's almost 0.055. Now at T equal to 50 Kelvin, it would be 3 into exponential minus 0.8 around P1 by P0. That is 1.35. So it's, as you increase the temperature, you can see this things are like the rotational terms become more prominent. The higher the rotational states at higher energy states become more prominent. At 300 Kelvin it will become more, actually 3 into exponential, it will become around minus 0.133. It will give you around 2.63. Okay, so as you increase in the temperature, the population will more shifted towards the higher energy states. Okay, so this is a problem. Okay, so in this problem we have to calculate the population ratio. So for that we write this population ratio. So in the problem actually only the theta is given. The population ratio, the whole energy expression we have written only in terms of theta r and the temperature that is applied. And after doing that we have for this system the states were between 0 and 1 state. So j equal to 0 and j equal to 1. So after doing that we will be getting the ratio of the population. The expression of the ratio of the population looks like this, and E1 is E0 is simply this. So after substituting this, these are the population fractions expression you are getting. Now from here you have to calculate for different temperatures, right? So first we have done is T equal to 10 Kelvin. So for T equal to 10 Kelvin, these are the ratio of the population in first and ground. For T equal to 50, this, as you gradually increase the temperature, the more the particles, the system, the more particles are shifted towards the higher rotational levels. Okay, so this is a problem. So this is done. So for today, this was the last problem. Okay, so thank you. So I'm ending the meeting.